And then, okay, so then I also take n to be as any subset of x. So then we say that n is at mu null set, and null that is just stated null. If n is actually in the sigma algebra and it has a measure of 0. And then we should also use, and this is something the book does it slightly differently, but let me do it this way. I say that n is a mu sub null set. If there exists n prime in A, which is a proper null set, such that n is contained in prime. And so we know various things. We know all subsets of a mu null set are mu sub-null sets. And if you look at the literature and see how is a null set defined, then in many cases you will see that this definition here would be the definition of a null set. But I can agree with the author that it may be convenient to say that this is a null set, but this is very important also. So therefore we give both of them a name. And it's very subtle. I will explain a little bit about the difference between these two things. But let me first take some examples. And the most interesting case perhaps is where we consider the Borel sigma and prime in the pigment. In this case, or maybe I should say in general, this will be an example. 0 or empty set is a mu null set. So for any measure space, the empty set is a null set. Here, so of course also the empty set is a null set. Some other null sets we have seen are, for example, natural numbers, integers, rational numbers. They are lambda null sets. These are also Borel sets, and they have lambda measure 0. More generally, all countable sets subsets of R are lambda null sets. And it could be, it somehow would sound believable if you didn't think much about it, but this was the end of the story. That a subset of the real number is a lambda null set that has an effect measure 0 if and only if it is countable. That may sound plausible, but it's wrong. So they exist uncountable lambda null sets. For example, the so-called Cantor set. And I will not go into detail about this. It is, maybe you have heard about the Cantor set. Have you heard about the Cantor set? Some of you. So roughly what you do is you take the interval from 0 to 1, and then you take the middle third, erase it, and then you take the middle third here, erase, and then you take the middle third here, erase, times, you'll end up with a set which has lambda makes it 0 and is uncountable. This is such a set here. And then something even more subtle. There exist subsets of a Cantor set that are lambda sub-null sets. And of course they are, because every subset of the Cantor set is a null set, so every subset would be a Cantor, would be a lambda sub-null set, but which are not array. And hence they are not null sets. So they exist sub-null sets which are not null sets. And this is what makes this theory a little bit complicated. And it's complicated also because it's really difficult to exhibit such sets. So the morale of the story is that these sets exist, but most of the sets you will encounter in real life, which are null sets, are proper null sets rather than sub-null sets. Okay. So this was a Cantor set. So in some sense, it's not a difficult definition. A null set is just a set that has measure 0. A sub-null set is a subset of a null set. So then comes the next thing, that is we have null sets and we have almost everywhere. So let's look at it. Suppose that pi of x where x runs to x is a property. Property in Danish egenskab or oversam proposition. Then we say that, and I'll give examples, this is a little bit abstract. This is true mu almost everywhere. Definition, it looks a little bit funny, but if and only if, and here comes the set x such that pi of x is false, is a mu sub. So what do we have here? So if we have such a statement like this, it is true if it is true for all x. This is how we should think about it. And it is close to being true if the set of x's that makes it false is very small. And what you should think about is that null sets and sub-null sets are small sets. They are sets that you basically can ignore. Another way of looking at it is supposing that your space is a probability space. Then each subset is like an event that has a probability. If the event is a null set, the probability is 0. Probability 0 means it doesn't happen. So if a statement is true almost everywhere, then the chance that the statement is true is equal to 1, it is 100%. So this is another way of looking at it. So let us look at the most interesting example of this is the following. Oh yeah, by the way, I had something here which I should explain. So mu AB is an abbreviation of mu almost everywhere. It also has a Danish, we say mu NO, which is mu næsten overalt. I think each language has translated this concept. It is so important. And Swedish, Norwegian, French, German. I don't know all the translations, but this is in English, our course, so we say AE for almost everywhere. Næsten overalt. So the most important example is the case where we have two functions, and they could, or perhaps they could go into a set y. Y could be maybe the reals or the extended reals or anything like that. Then we say that u equal b, mu almost everywhere. That means precisely the same as what we have here. That means that the set of x, where u of x is different from v of x, is a subnull set. Mu subnull set. And this is really where we most often shall use the notion of almost everywhere, but we will also see it in different contexts. And so what we really do in this chapter here, subchapter, and the course is that two functions which are equal almost everywhere are, for all practical purposes, identified. We almost think of them as being the same function. This is somehow the trick we should use. We don't use in this chapter, but later on, this is how we will think about it. Two functions which are equal almost everywhere. We say they are, for all practical purposes, the same function. And also, if you have such two functions which are equal almost everywhere, their intervals will be the same. Even intervals over any subset will be the same. So they behave identically as far as integration goes. And this is something we will prove. So this is what you should think about, and we're trying to formalize this idea. This is what is happening in this chapter. I want to make a note also about this distinction between null set and subnull sets. A further note, suppose that n is a mu subnull set. And this is a little bit exotic null set, as I already indicated. And suppose also that n is actually measurable. Then n is a proper null set. And this is easy to see because if that was the case, if it is a subnull set, then there exists an n prime, so that n prime is measurable and has measured 0. N prime is a proper null set. So if I want to prove that n, which is assumed to be a mu subnull set, if it is a proper null set, okay, I know already by assumption it belongs to A. I have to show that mu of n is 0. So what I know is if it's a subset of something that has measured 0, then it itself has measured 0. And this is because measure is monotone. So if this holds, then mu of n is less equal to mu of n prime, and this was 0, and this implies mu of n is 0. So the next thing we should note in the context up here is that if u and v go from x to y are measurable, then the set of x where u of x is different from v of x is also measurable, say it belongs to A, where A is sigma epsilon, sigma x. Hence, this set here will be a proper null set. Null set if the two functions are equal mu almost everywhere. So this is another situation where even if we define a notion of subnull sets, then most often what we encounter are proper null sets. Okay, so maybe enough said about that. Yes, and then we have another. further that either it is positive or it is nil one. That means in both cases we can integrate the function. These are the two requirements needed to ensure that we can integrate the function. In that case, we define the integral over a of u divided to be the usual integral of u times the indicator function of a, and then we integrate that function. So the integral over a measurable subset of a function is simply defined in this way here. And in particular, we see that if we put a equal to x, and we use an indicator function for x as just constant equal to 1, then we see the integral over x u in u is equal to simply 2 u. Because what we have here is just multiplied by 1. Okay. With that said, we can move on and show some properties. And the properties all have that in common that what we are somehow zooming in on is that if we have two functions which are equal almost everywhere, then we behave identically as far as integration goes. This is what we try to do. And we need first inequality, call it an Markov inequality, and I have to warn you that I do things slightly differently than in the book. I think I made some notes about it. You know, I mentioned the same results, but I prove things a little bit differently. I make some shortcuts here and there. So we have a nice result saying that if I have an integrable function with respect to mu, and we have the same measure space as always, and if we have some positive number c, then, and I have to make another convention. The set of x so that u absolute value is greater or equal to c, and now we explain what this means, is greater or equal to 1 over c times integral of u absolute value. Like this. And this is overall mistakes. So what do I mean by this? And by this I simply mean the set of x so that u of x absolute value is greater or equal to c. So I think this is a custom in probability theory that you don't put the variable here. It is somehow understood. And I hope you agree with me that this set here looks nicer to write like this and like this. It's a little bit, if this x, it makes it a little bit, I don't know how to look at this formula. So this is a very elegant way of writing it, but of course you have to understand that it is understood that it is x there. So this is a very common notation, and the book definitely uses this kind of notation, and this is what it means. So the inequality says that the measure of this set here is greater than this number here, and this is integral over all of x. It might very well be right. Let's see. Smaller s. Thank you. Thanks a lot for that. Okay, so let's just see why this true. It is not hard to prove.